Hey everybody, welcome back. This week we're going to be going over some basic calculations using mole-to-mole ratios, so be sure you have the following materials ready to go before we begin. Your mole-to-mole worksheet from Canvas, a writing utensil, and a calculator. I'm going to be doing a bunch of mole problems so you can really get a handle on these because they're going to be very important for the next part of our lesson when we go over mass-to-mass problems. Chemical equations are like recipes. Whenever you're making something in the kitchen, you follow certain ratios. For instance, if we were making a proper s'more, we need 3 mini chocolate squares for every 1 roasted marshmallow. This is called a conversion factor for mole-to-mole ratio. I can write this out with 3 chocolates on top for every 1 marshmallow on the bottom, or I can flip it and I can write 1 marshmallow on top for every 3 chocolates. But either way, it is telling us that in order for one s'more to be made, I need to have 3 chocolates for every 1 marshmallow. Now let's take this same concept and apply it to a chemical equation. Remember that the coefficients are what tells us the number of moles, or in other words, the amount. If there is no coefficient in front, that represents a 1. And if it makes you feel better, you can actually just write that out in front there so that you have it. If we were to write the conversion factors for the mole-to-mole ratio between ammonium and hydrogen, then we would apply the same concept. The chemical equation tells us that for every 3 moles of hydrogen, we produce 2 moles of ammonia. And we can write this the other way as well by saying 2 moles of ammonia is equivalent to 3 moles of hydrogen. Either way, this conversion factor is telling us that for every 2 moles of ammonia, I need 3 moles of hydrogen. Let's look at the mole-to-mole ratio between ammonia and nitrogen gas. The coefficients tell us that for every 1 mole of nitrogen gas, we can produce 2 moles of ammonia. Or we can reverse this conversion factor and say that for every 2 moles of ammonia, I need 1 mole of nitrogen gas. Either way, it tells us the same thing. Let's take this concept of conversion factors and apply it to an actual problem. So if I have 0.172 moles of bromide, I want to know how many moles of sodium bromide I can produce. So I'm trying to go from bromine to sodium bromide. If I have 1 mole of bromine, I can produce 2 moles of sodium bromide. And remember that I can write this either way. Say 2 NaBr on top is equivalent to 1 Br2 on the bottom. And both ways are telling me that for every 1 mole of bromine, I can produce 2 moles of sodium bromide. Well, if I only have 0.172 moles of bromine, how many moles of sodium bromide can I produce? I'm going to look at which conversion factor to use. Since I'm given bromine, that's what I want to get rid of. So I'm going to put bromine on the bottom, which means that this will be the conversion factor that I'm going to need to use. I'm going to put 1 Br2 on the bottom and 2 NaBr on top. Whenever you're trying to decide the conversion factor, you always put what you're given on the bottom and what you're trying to get to on the top. That's how you decide what conversion factor to use. If I were to plug this into a calculator and say 0.172 times 2, that's going to give me 0.344 as my final answer. Now let's take a look at the second problem. If you feel like you've got the hang of it, go ahead and pause this video and attempt it on your own. If not, continue watching. I want to know how many moles of sodium iodide are needed to produce 0.67 moles of iodine. So if I'm starting with 0.67 moles of I2, I need to figure out what conversion factor to put on the top and bottom. I know from looking at the coefficients that for every 2 moles of sodium iodide, I produce 1 mole of iodine gas. And I can reverse that and write it out as either way. So finish writing this out. And so looking at this, if I have I2 as my given, that's what I want to put on the bottom. So this will be the conversion factor that I plug in. And so I'm going to say 1 mole of iodine gas is equivalent to 2 moles of sodium iodide. And it is asking me to find moles of sodium iodide, which is on top. So I've done that correctly. I'm going to plug that into my calculator. And I end up with 1.34 moles of sodium iodide as my final answer. Whenever you're solving for these multiple and later on mass-to-mass problems, you always want to make sure that your equation is balanced. This is the most important step because the balanced equation is what tells you the mole-to-mole ratio. Always figure out what unit you're given to start with and then what unit you're trying to find in the end. From there, determine what your conversion factors will be and then plug and chug to solve the problem. If you feel like you understand these multiple problems, feel free to skip the rest of the videos and complete the practice problems on your own. Then begin watching the mass-to-mass section of this video. If you think you still need some more practice, that's okay. Continue watching and we will go through more problems together. This next problem is asking me how many moles of oxygen can be consumed if I have 79.6 moles of carbon dioxide. So once again, I'm going from oxygen and carbon dioxide. So I need to pay attention to these coefficients. I know in my problem, I'm starting off with 79.6 moles of CO2. So that's what I'm going to put on top. Now I need to figure out what conversion factor to use based off the 2 elements or compounds that are given in the problem. In this case, I'm going between oxygen and carbon dioxide. So that for every 7 O2, there are 4 CO2s produced. And I can write this out either way and put 4 CO2 over 7 O2. My equation has CO2 as my given. So that's what I want on the bottom for my conversion factor, which means that this is going to be the conversion factor that I plug into my equation. And I can write that out as 4 CO2 on the bottom and 7 O2 on top. I know that's correct because it's asking how many moles of oxygen, and that's what's on top at the end. So once again, I'm going to plug and chug into a calculator and do 79.6 times 7 divided by 4. So everything on top gets multiplied and is divided by everything on the bottom. So I do 79.6 times 7 all over 4. Once I plug that into a calculator, I end up with 139.3 oxygens. This next problem is asking how many moles of C2H6 would be necessary to form 15.6 moles of water. So I'm going from C2H6 to water. Once again, I'm going to start by writing out my given, which is 15.6 moles of water. Your given is just whatever number is given to you in the problem. So if I have 15.6 moles of water, I want to figure out how many moles of C2H6 I'm going to end up with. So I know that whatever conversion factor I have, C2H6 is what needs to be on top. I can write out my conversion factors by looking at the coefficients. For every 2 C2H6, I produce 6 H2Os, and I can write that out either way, 6 H2Os over 2 C2H6. But remember, if I have H2O on the top here, then that's what needs to be on the bottom for my conversion factor, which means that this is the one we're going to plug in. It also has C2H6 on top, which is what I wanted. So I'm going to put 2 C2H6 over 6 H2O. And when I have that, I'm going to plug it into my calculator. which would give you 5.2 moles of C2H6 for your final answer. It's always better to break it down into multiple steps, especially if you're using the calculator on your phone. In this next problem, before we begin, I want to draw the attention to the fact that this equation is unbalanced. Before we can begin solving mole-to-mole problems, you have to have a balanced equation because that's what tells you your mole-to-mole ratio. So go ahead and pause this video and try balancing this equation on your own. If you are still struggling with balancing equations, please review the week 5 module. Your final balanced equation should look like this. We are being asked to calculate how many moles of the product form when 0.028 moles of potassium reacts completely with it. Remember that the products are anything on the right side of the arrow. So in this case, we're asking to compare potassium oxide with potassium. We will start with 0.028 moles of potassium on top. And our conversion factors will either be 4 moles of potassium to every 2 moles of potassium oxide, or vice versa. In this case, we want to find the conversion factor that contains potassium are given on the bottom, and our product, which we want, on top, which is potassium oxide. In this case, it will be our second conversion factor. So I'm going to plug in 4 and 2, and then I can plug and chug into the calculator. When I do that, I find that for every 0.028 moles of potassium, I only produce 0.014 moles of potassium oxide, my product. Go ahead and pause this video and complete the last problem on your own for the mole-to-mole worksheet. Then continue on for mass-to-mass. In this next part of the lesson, we're going to be going over mass-to-mass problems. This is actually taking what we just learned with mole-to-mole and combining it with what we learned last week about molar mass to go from the mass of one compounder element to the mass of a different compounder element. It sounds complicated, but it actually follows the same pattern, or as I like to call it, roadmap. Every single time. You always start with your given mass. Then you use its molar mass to convert it to moles. And once you have moles of your given, you use that mole-to-mole ratio, which we've been practicing with, to convert it to moles of what it's asking for elements and compounds. Then you take it one step further and find the molar mass of what you want and use that to convert to grams of your substance that it's asking for. Be sure to check out some of the other YouTube videos I've posted on Canvas if you're still having a hard time with this concept. In this problem, it's asking me to go from 45.75 grams of ammonia to grams of dinitrogen tetrafluoride. Anytime you see grams, you're going to need to use the molar mass for each of these, just like in our roadmap. I'm going to use the same roadmap and plug in my numbers. I'm given 45.75 grams of ammonia, and I'm going to use the molar mass of that substance to convert it to moles. So I know that for every 1 mole of ammonia, that is equivalent to 17.031 grams. I get that from calculating the molar mass using the periodic table. Once I've done that, I can find the number of moles of N2F4 by using the mole-to-mole ratio. So I'm going to put NH3 on the bottom and N2F4 on top, and I'm looking at my coefficients. I'm going between NH3 and N2F4. So in this case, there's 2 NH3 and 1 mole of dinitrogen tetrafluoride. So I've converted from mass to moles. Now I've gone from moles of my given to moles of what I want. My last step is to convert to the mass of what I want. So once again, I'm trying to find grams of N2F4, so that's what I'm going to put on top. and I need to find the molar mass of that compound. So I'm going to use the periodic table, and when I do that, I get 104.01 grams. Now the very last thing for me to do is to plug and chug all of this into the calculator. So I'm going to multiply everything on top, write that down, and then multiply everything on the bottom and do the same thing. On top, I end up with 4,758.46, and on the bottom, I end up with 34.06. Now I can plug these two numbers into the calculator. I end up with approximately 139.71 grams of dinitrogen tetrafluoride. So this is my final answer for this problem. I know that if I have 45.75 grams of ammonia, I can produce 139.71 grams of dinitrogen tetrafluoride. Once again, I'm going to do the same type of problem, a very similar problem, but this time I'm trying to go from NH3 ammonia to hydrogen monofluoride, or hydrofluoric acid. I'm going to go ahead and write down what conversions to use for each of these. This is a good practice to get into, just so that you remember what conversions to use. Once again, I'm starting off with 45.75 grams of ammonia, and I'm going to use the molar mass of that substance to convert it to moles. So I know that for every 1 mole of ammonia, that's equivalent to 17.031 grams. Next, I need to find the mole-to-mole ratio between ammonia and hydrofluoric acid. Remember, you're always looking at the coefficients. In this case, I'm going to put 2 moles of ammonia on the bottom is equivalent to 6 moles, or produces 6 moles of hydrofluoric acid on top. So that is my mole-to-mole ratio, which I've put right here. Now my last thing is to find my molar mass of what I want. In this case, that is grams of hydrofluoric acid. So I'm going to find that molar mass, and I know that's equivalent to 1 mole of that substance. The molar mass of hydrofluoric acid is approximately 20.01. And once I found that, I'm going to plug everything in and then divide. So I'm going to do 45.75 times 1 times 6 times 20.01, and I'll write that down. When I do that, I end up with 5,492.7. And that's all over 17.031 times 2, 34.06. Now I can plug these last two numbers into my calculator, 5,492.7 over 34.06. And when I do that, I get 161.3 grams of hydrofluoric acid for my final answer. This last problem, I did not put the roadmap, however, it follows the exact same pattern as the previous two. I'm starting with 100 grams of propane, which is C3H8. I want to know how many grams of carbon dioxide will be produced. I'll start by putting 100 grams of that propane and finding the molar mass. The molar mass is 44.097 grams, and that is equivalent to 1 mole of that compound. Next up is to use that mole-to-mole ratio. Remember, if there is no coefficient, that is equivalent to 1 mole. So I know that there's 1 mole of C3H8 for every 3 moles of carbon dioxide. And finally, it's asking how many grams of carbon dioxide are produced. So once again, I'm going to use the molar mass, this time of carbon dioxide. When I plug that in, I get 44.0 0.01 grams, and that is equivalent to 1 mole of that carbon dioxide gas. Now that I have all three conversion factors, I'm going to plug it in, everything on top divided by everything on bottom. 13,203 on top, all over 44.097, which is 299.41 grams. As I've said before, this can be a confusing topic. It requires a lot of practice. If you feel like you're still struggling, please sign on to office hours and we can work through more problems together and we can break it down at a slower pace. If you feel like you have a good understanding, make sure that you complete the last problems for the mole-to-mole worksheet as well as the last two problems from the mass-to-mass worksheet. Make sure you upload both on Canvas to receive full credit for the week. The important thing with these worksheets is that you are showing your work. If you do not show your work, you will not receive credit. Even if you claim you know how to do it and you plugged it all into a calculator, I will not give you credit unless your work is actually shown. So make sure that you're showing me what exactly you're plugging into a calculator. Since this is our penultimate week, next week's work will actually be uploaded this upcoming Monday. The work will only be for a half week. However, I want to make sure that you have time to get it completed. It must be turned in by Friday, May 29th to receive credit. All the work for term 4 is due by that date, May 29th at 5 p.m. Grades are due that day, and I will be submitting your term 4 grades into the grade book on Aspen. If you do not turn things in by that time, then I cannot accept them later on. As always, I love you guys and I miss you. I hope that you're doing well. Please reach out if you have any questions or you just want to talk. Please stay strong, keep working hard. You've got 2 more weeks and then you can just relax and enjoy summer. Bye.